All right, let's go ahead and get started. Everybody's thinking about spring break, including me. But we have to do lab on Wednesday. So lab 6 on Wednesday, please don't forget. We had an exam last week, if anybody remembers. High score was 104. Class average was about 70s, mid-70s. That's actually very good for this exam. It is. You should check your overall grade now on Blackboard. If you have 160 or more points, you're doing very well and you have a good shot at getting an A. When you click on overall grade or when you see it in the corner, it'll look something like this. It'll have a number slash another number, and it'll be color coded. Color coding, I think, is just to depress you.
Yes, the third one.
The first number are your total points. The second number is nonsense. So is the color. Simply ignore the second number. All you care about is your total points. Any questions? There was one question on the exam that people had difficulty with in general, and it was the Lewis problem. So let's do this very quickly. We have C3H6 with a carbon-carbon double bond. Now, again, I do this pretty much by inspection, so we'll do it my way, and then we'll do it with the rules. So, we look at the periodic table. Carbon is here in group 4. It has 4 valence electrons. The hydrogens are group 1. So, let's put our 3 carbons up. And here's our hydrogens. Now, we read the problem. We have a carbon-carbon double bond. So let's make the double bond first. We have lots of miscellaneous electrons laying around. Let's just grab a couple, move them in, and we have a double bond. Now, we have to put the hydrogens in. To add the hydrogens, they each have one unpaired electron, one valence electron. And there's lots of unpaired electrons in this molecule. In fact, there are 6 of them. So let's just take and stick the hydrogens on. And here we are. Now, if we look at our central carbon, we have 2, 4, 6, 8 electrons. This guy also has 2, 4, 6, 8 electrons, and so does he. Every hydrogen has 2, which is because it's in the first period, that's all it can hold. And this is the organic molecule protein. Any questions? Now the rules have more steps. According to the rules, first you count the valence electrons and the number of hydrogens. Well, we're in group 4. We have 3 of them. 3 times 4 is 12. 6 hydrogens, total 18 electrons, and our 6 hydrogens. Secondly, we're going to draw a central atom, that will be the carbon, and we're going to stick the others on, not the hydrogens, and give them an octet. So we have something like this. Now we count up the electrons. We have 6, 12, that's 16, right? Yeah, 16. And we have 2 left over because we had 18 electrons. So we put these on the central carbon. Now, The rules say we look at this, make double or triple bonds to give the central atom an octet. Right now it is 2, 4, 6. Move these guys in, and we have an octet on the central atom. So we're good. Finally, we're going to add the hydrogen back. And once again, we have protein. Any questions? All right. Well, let's go ahead and start then on Chapter 5. Chapter 5 is chemical reactions. Lab 6, believe it or not, is also chemical reactions. They finally got them coordinated. This is one of the most favored reactions to do as a demonstration. Is the thermite reaction. Take aluminum, iron 3 oxide, they react to give molten iron and aluminum oxide. The thing that makes it so neat is that it really burns with great vigor. People in the front row get burned with sparks, so do you if you're doing it. It's yet another one of these that we can't do here. But nonetheless, it's a wonderful demonstration. We have a film clip of this in a minute. Chemical reactions. We've seen this before. Bromine reacting with aluminum metal to give aluminum bromide. We know we connect reactants and products with a reaction arrow. The reaction arrow, we said, has the properties of an equal sign. That means there must be the same numbers and types of atoms on both sides of the equation. Here's our chemical equation for this reaction. Couple things to point out here. We have numbers that are called coefficients in front of some of them, and we have little letters. The equation tells us with the coefficients, there are 2 aluminums, 3 bromines. Here we have 2 aluminums and 3 bromines. 6 bromines. 2 times 3 is 6. 3 times 2 is 6. Same numbers and types. The little letters reflect the physical state. They're optional. Sometimes they're shown, sometimes they're not. S is solid, liquid, gas. AQ is aqueous solution. It means something's dissolved in water. Now the coefficients describe what's called the stoichiometry of the reaction. Stoichiometry is a neat word. You can say it in front of people, they think you're smart. Really, it's just the number of moles of each reactant. This tells us there are 2 moles of aluminum that react with 3 moles of Br2 to give 2 moles of aluminum bromide. You'll also note we can replace moles with mass. Well, this would be 54 grams of aluminum, 479 grams of bromine, 533 grams of product. And if you're doing this in your head, you'll note that this plus this gives that. Conservation of mass. Talked about that in Chapter 3. All right. The coefficients. The coefficients are numbers that you put in order to ensure that you have the same numbers and types on both sides. This is the process that's called balancing the chemical equation. Now, there are lots of ways to balance chemical equations. There are little computer programs that will do it for you. I do it by inspection using what I tend to call an odd-even method. We'll see that. Let's go ahead and look at an equation. This is hydrogen peroxide. Hydrogen peroxide decomposes to give oxygen gas, O2, and water. You'll note that this equation is not balanced, however. We have two hydrogens. That's good. But we have two oxygens and 1, 2, 3 oxygens on this side. I look at this and say the number of oxygens here are odd and these are even. First thing I always strive to do is to make it even on both sides. 2 oxygens on this side, 3 on this side. Simplest way to make this even would be to put a coefficient here in front of this water molecule. So let's stick a 2 in here, and there we are. Now, when we stick in coefficients, we also mess with other atoms as well. We now have 4 hydrogens here, only 2 hydrogens on this side. We can fix that, however, by sticking a number 2 right here. Now, we have 4 hydrogens, 4 hydrogens, 4 oxygens, 1, 2, 3, 4 oxygens. 4 hydrogens, 4 oxygens on each side. We have balanced the equation. Any questions? Well, let's do another one. The way to learn to balance equations is by doing, we'll see that in a minute. We just had exam 1, so we're well versed in converting chemical names and structures. Potassium chlorate, even without your 3x5 card. We remember that chlorate is ClO3, parent of the chlorine family, and has a charge of -1. Potassium is here in group 1. It has a +1 charge. So we have potassium +1, chlorate -1, KClO3. And it says solid, so I put the S in. We're going to decompose this by heating it to give oxygen gas and potassium chloride. Remember, oxygen is one of our diatomics. So oxygen gas refers to O2. Potassium chloride, this is +1, this is a halogen, it's -1. So simply KCl. Now once again, we note this is not balanced. We have 3 oxygens here, 2 oxygens on this side. So what I would do is I would say, all right, let's make them both even by sticking a 2 in front of here. There it is. Now, by putting our 2 in, we have introduced 2 potassiums, 2 chlorines, and now we have 6 oxygens. And we have 2 on this side, so we need 6 oxygens, that gathers 3. Again, we have 2 potassiums, 2 chlorines, only 1 on this side, double this, and by George, I think we're there. We have balanced the equation. Now this is actually a very useful little reaction that we do in lab because it's a nice way to make a small amount of oxygen gas. Sometimes you're doing a reaction, you need pure oxygen, take potassium chlorate and heat it up and bubble your oxygen in. This is also the reaction that is known as the gummy bear reaction. This is a gummy bear. This is potassium chlorate. We're going to heat it. It's going to make oxygen and KCl. Now, a gummy bear is basically sugar. When we heat up the potassium chlorate, it's going to also heat up the sugar here, which is going to react instantly with all this oxygen that we're making. The products will be CO2 and water. So, let's see what happens here. I'm going to take our little gummy bear. This is hot potassium chlorate.
Ouch!
We add them together. The sugar is reacting violently with the oxygen. And when we're done, we have released our CO2 and water vapor, and we're just left with potassium chloride. Any questions? Kind of a fun thing to do in there. All right, let's go ahead and look at a set of real reactions and practice balancing these. Now, I would really love to be able to write on this board, but I can't. Oh well. So we'll fake it. Pretend I'm writing here. Our first reaction. We have 2 hydrogens. We have 3 hydrogens. First thing I would do is double this, put a 2 in front. Okay? Now that's going to give us 2 nitrogens. That's what we've got, so that's good. It also gives us 2 times 3, 6 hydrogens, so we need a 3 in front of this guy. So, if I've done this correctly, 3 hydrogens into 2 abundance. Go ahead and take a look at this guy, and then we'll do it. We have 1 zinc and 1 zinc. 1 hydrogen, 2 hydrogens. So I'm going to double my HCl. That's going to give me 2 hydrogens and 2 chlorines. We have 2 hydrogens and 2 chlorines on this side. I think we're done. Look at the next one. It's a little more complicated. We have 3 oxygens, we have 2 oxygens. I would double this. By doubling it, I now have 4 irons. We have 1 here, so I need a 4 in front of the iron chloride. By doubling this, I have 6 oxygens, so I need a 3 here. Numbers of chlorines. We have a 4 on this side. 4 times 3 is 12. We would need 6 chlorines. So if you're keeping score, yep, looks like that. Any questions? Another. And we have 2 hydrogens on this side, 1, 2, 3 on this side. Simplest way to make it even hydrogens would be to double the sodium hydroxide. If we do that, we need 2 sodiums on this side. That gives us a total of 4 hydrogens. Only have 2 on this side. Gotta double that. Yep. Next one is very easy. One lead, 1 chlorine, 2 chlorines. 1 hydrogen, 2 hydrogens, simply double the HCl. Finally, when we're doing problems here with polyatomic ions, just treat these as a unit. Don't break it down into 1 nitrogen, 3 oxygens. It's just a lump. So we have a nitrate, we have 2 nitrates. We're going to have to double this. If we double that, we're going to need 2 silver chlorides. 2 silvers works. 2 chlorides, well, that's what we've got here. So, yep, that works. Any questions? Now, there are a couple tutorials in this chapter, maybe 3. First one is called balancing chemical reactions. This is the organic molecule ethene, reacts with oxygen, and it gives CO2 and water. As I look at this, I have 2 carbons on this side, 1 on this side. So let's double the CO2s. Now, we have 1, 2, 3, 4 hydrogens. We only have 2 here, so we need to double that. And finally, oxygens. We have 1, 2, 3, 4, 5, 6. We need 3 O2s. There is one thing, because this hasn't come up and said we're correct yet, has it? On the tutorial and on Blackboard. Blackboard is most important, of course. These are blanks that you fill in. You must not leave an empty blank. We don't usually put a coefficient of 1 in, but here we must. Both on Blackboard and on the tutorial. Let's do another. This is another neat reaction. Calcium carbide reacts with water to make acetylene gas. Now this is the gas that you use in blowtorches for metal cutting and welding and stuff. And also you make calcium hydroxide. Acetylene burns, obviously, blowtorch gas. This reaction was actually used in coal mines a long, long time ago. Helmets were designed with a little bit of, well, a little button here you could push. Calcium carbide would dribble into some water, and you would light your helmet on fire. And that way you could see down in the deep, dark mine. Problem is that they fill up with methane gas, and if you go down and light your helmet, you can explode. You don't want to do that either. So going down in the mine shaft, you would take the canary, because canaries would die very suddenly from methane gas. And if the little bird lived, then you could light your helmet. Yeah, whatever. Glad we don't do that anymore. So let's go ahead and balance this. 1 calcium, 1 calcium. 2 carbons, 2 carbons. We have 2 hydrogens, 1, 2, 3, 4 hydrogens. We have to double this guy. And I think that's all we need to do. Now remember, if this was blackboard, you would have to put a 1 here, here, and here. Now I grew up in the 50s. There were fun things that happened in the 50s. A lot of things that weren't fun, but there were some fun things. This is one of them, called a bang sight cannon. Yeah, everybody had one, okay? You would put water down in here. When you push this little button, calcium carbide would dribble down into the water. The chamber here would fill with acetylene gas mixed with air. This is a spark device. You punch this down, it sparks, and it blows up. You could stuff all sorts of crap in the barrel here, shoot it halfway across the room, across the yard. Looks like this. Such an amazing little toy. You can't, well, you can get antique versions of them now, but you used to be able to just go and buy calcium carbide anywhere. Whatever. Like I said, the way to learn to balance equations is by doing it. There is no credit for this, but on Blackboard, there's a page with lots of reactions and a page with the answers. So you can, these are pretty much comparable to what you would see on the exam. We will balance at least one equation on the exam. What we got? We're good, right? All right, let's move onward. Types of chemical reactions. Sounds a little bit like biology because we're putting names on things, but we'll see that this can be useful to us. Synthesis, decomposition. In a synthesis, we're taking 2 or more things and we're making a new substance. Decomposition, we go backwards. Example of a synthesis. Here we take carbon, reacting it with oxygen to make CO2. Think of barbecue. This is called synthesis from the elements. We can also do it from compounds. The organic molecule ethene reacts with HBr to make bromoethane. Again, 2 guys, 1. Decomposition is just backwards. This is copper 1 sulfide. If you heat it up, you get copper metal by George, and of course sulfur gas. Decomposition into elements. We can also do it with compounds. Calcium carbonate. This is limestone, right? If you heat it up, it goes to calcium oxide and evolves CO2. Now this reaction is actually kind of neat, very useful, because it's usually run in the reverse direction. That is, if you take calcium oxide, put it in a room full of CO2, add a little bit of dirt, maybe some gravel. What do you get? Well, you get your limestone mixed with dirt and gravel. We call that cement. This is the cement reaction. Any questions? All right. Single and double replacement, sometimes called displacement reactions. In a replacement, 2 compounds or an element in the compound react so that the elements or ions are switched. Now, what does that mean? This is a single replacement. In a single replacement, you take an element and a compound, you react them, and you make an element and a compound. What has happened is the nonmetal from the element has replaced the nonmetal in the compound. The rule is, in general, nonmetals replace nonmetals, metals replace metals. It's a general guideline. We'll see there are exceptions. Single replacement reaction, again, the key thing to look for, element in a compound, element in a compound. In a double replacement reaction, what we're doing is simply swapping ions. These occur in aqueous solution. If you take silver nitrate and sodium chloride, mix them together, you get a solid form, silver chloride. You also leave sodium nitrate in solution. In order for a double replacement reaction to occur, something insoluble must be formed, or you must form a gas. So these are also called precipitation reactions. Any questions? Oxidation and reduction. One or more atoms undergoes a change in oxidation state. Okay, what does that mean? Carbon, oxygen, CO2. In a bit, we will talk about the rules for assigning oxidation numbers. But we still know some from chapter 3. In chapter 3, we said all elements have an oxidation number of 0. We said that whenever you had oxygen in a compound, it would be -2. So if this is -2, we have 2 of them, that's 4 negatives. The carbon must be +4. We have started with carbon with a 0 oxidation state. It went to 4+. Oxygen went from 0 to 2-. That is what's called a redox reaction. Redox, oxidation, reduction. You'll note that this is also synthesis. Many synthesis reactions, not all of them, but many of them are also redox. Any questions?
So was it react like a redox state? What's redox mean?
Redox is reduction oxidation.
Oh, okay.
But, we'll talk a lot more about redox in a couple minutes.
Okay, thanks.
Let's look at these, see if we can assign them as synthesis, decomp, or replacement. Here we have hydrogen reacting with nitrogen to give ammonia. We are taking 2 things, we're making something new. This would be a redox reaction as well, but right now we'll just call it synthesis. Element and a compound, element and a compound, the key signature for a single replacement reaction. The nonmetal has replaced the nonmetal. Here we have sodium sulfate, barium chloride. We mix these together, we get barium sulfate as a solid, and sodium chloride stays in solution. We have swapped ions. Sodium has paired with chloride, barium is paired with sulfate, and it's insoluble in water. Classic double replacement. Any questions? Look at these guys. We started off our discussion with this. Peroxide decomposes, doesn't it? You give oxygen and water. Simple example of a decomposition reaction. However, this is not balanced, is it? Remember how we balance it? We have even number of oxygens. Here we have an odd number. I would double this. When we double the waters, we need 2 peroxides. Oh, I thought it showed you the balance. Shoot, I meant to do that. All right, well, let's just ignore that. Let's do this one. People look at this, the first thing they want to say is single replacement. But it's not, is it? 2 guys making 1. Simple synthesis reaction. And finally, this one was on the slide earlier, and it is balanced. We have an element and a compound. We're making an element and a compound. Non-metal replaces non-metal. It's a single replacement. All right, why do we care about naming these reactions? Well, when you take and you mix things together, you never quite know what's going to happen. And so you need some basis to make a prediction. By knowing if you have decomposition, synthesis, single or double replacement, you can pretty much guess what the product is going to be. For example, we've seen this before. Aluminum reacting with bromine, we will make aluminum bromide. We know that. This is a synthesis reaction. It involves a metal, right? So, because we're dealing with something that's going to produce a product that's a metal, it's going to be an ionic product, isn't it? So if we take add our aluminum to the bromine, let this thing burn down. Very nice violent reaction. Very toxic gas. The solid that forms inside the beaker and around the top here is going to be our product. It's going to be ionic. So we look at this and say, okay, aluminum is group 3. It'll be a +3 ion. Bromine is a halogen. It'll be a -1 ion. Our best guess here, and that's all we're doing, is our best guess. 3 bromines, 1 aluminum, aluminum bromide. Now this guy isn't balanced, is it? 2 bromines, 3 bromines. Let's double the aluminum bromide. That'll give us 2 aluminums now on this side. We needed 2 here. We have 6 bromine atoms. We need 3 BR2s. I think we're done. Any questions? All right, if we do a synthesis reaction where we have non-metals, what do? This is our balloon filled with hydrogen. The room is full of oxygen. We will take the flaming torch here. do that with it. Okay. What we want to do is look at our reactants, think about their valence electrons, how we're going to put this together, and make a best guess of the product. So, hydrogen has one valence electron each. The oxygen is group 6, so it will have 6 valence electrons. Quite obviously, we can pair these up this way, and we can make water. Again, we're not quite balanced. We need 2 waters on this side to get our 2 oxygens. This gives us 4 hydrogens. We need another 2 to find. Any questions? All right, this is my favorite in the whole series here. This is nitrogen triiodide. Now, nitrogen triiodide is what's called a contact explosive. That means you touch it, it goes boom. You make it by mixing ammonia dissolved in water with iodine solid. Just dump them together, shake it up. As long as it's wet, it's fine. Mix this black solid. Black solid will sink to the bottom, take and filter it off. These are pieces of filter paper with just a film of this stuff on them. All right. Let it dry. Now, we are going to touch these gently. In fact, we're going to touch them with a feather. Isn't that neat? And it's the boom. That's just touching it with a feather.
That's a fun part.
Now, decomposition reactions are, well, difficult to predict products, more so than the other types. But what you do is you explode yourself, and then you look for clues. The clue that I see here is the great big cloud of purple vapor. Iodine is purple. It has a very high vapor pressure and will just sit there in a little glass dish, giving off these purple fumes. So my best guess here is that iodine is one of the products. So things that explode tend to form nitrogen gas as well, because it's very stable. Our guess here is we're going to decompose this into the elements. So we're going to make I2 and N2. Remember, these are both diatomic elements. Now our reaction is not balanced. We have 3 nitrogens or 3 iodines. We have 2. Let's double that. That gives us 6 iodine atoms. We need a 3 here. We have 2 nitrogens. 2 nitrogens. I think that works. Any questions? Single replacement. Once again, you're going to predict our products. Again, metals will replace metals, non-metals replacing non-metals. If this was our classic single replacement reaction, we would predict that the chlorine would replace the chlorine. Lead is +4, it will stay +4. Fluorine replaces chlorine, and we will get Cl2. We are not balanced. 4 chlorines, 2 fluorines. We need to double this. Oh, okay, I double my fluorine instead. That gives us 4 and 4. We need 2 here, 1 lead, 1 lead. I think we're good. Now, the rule, metal replacing metal, non-metal replacing non-metal, is a very nice rule. But like most nice rules, there are exceptions. And it just turns out that in the world of single replacement reactions, the exceptions are probably the most important of the reactions. For example, if you take copper monoxide and hydrogen gas, you get copper metal and water. What we've done here is basically refine copper monoxide to copper metal. Here, hydrogen is acting as if it was a metal. It's not, but sometimes it likes to pretend. The other one that likes to pretend is carbon. Carbon can act as a metal and a non-metal. In this case, this is iron trioxide reacting with carbon. We get iron as our product and CO2. This again is a refining process. This is what they do in dairy. Big pots of iron trioxide mixed with coke, which is just carbon, to give molten iron and CO2. Any questions? For a double replacement, we're just going to switch cations and anions. And something must be insoluble. Potassium sulfate, barium nitrate. The potassium and the nitrate will exchange. Oops. Sorry. Potassium will exchange with barium. Barium will exchange with sulfate. And this is insoluble. Now, like I said, these are also called precipitation reactions. Precipitation reaction simply means that something falls out of solution. It is very slightly soluble or insoluble in the water. Here's an example. Potassium iodide, lead nitrate. We have them in separate containers here. When we mix these, we will get lead iodide, which is a solid, insoluble, and potassium nitrate, which stays in solution. So, let's watch it. Take some potassium iodide, simply squirt it in, get a lovely solid lead to iodide precipitate. Any questions? Well, there's one question that I'm sure is in the back of everybody's head, and that is, how in the world did I know that lead to iodide was going to be insoluble? Well, because I know the rules. The rules, solubility trends. You look at your compound. If it has lithium, sodium, potassium, or ammonium as the cation, it will be soluble, period. Doesn't matter what you pair it with. If the anion is nitrate or acetate, it will also be soluble, regardless what the cation is. If it's a metal halide, the halogens, remember, are group 7. Most of them are going to be soluble. There are a group that are not. We call these the heavy metals: silver, lead, mercury, and copper. They are insoluble halides. We just saw lead. Metal sulfates in general are soluble except for barium, lead, and calcium. Now, unless the compound is covered by rule number 1, metal hydroxides, oxides, and sulfides are going to be insoluble. The one sweeping rule here. One more sweeping rule: if it's not covered by rule 1, and it's a carbonate or a phosphate, it's also insoluble. So our insolubles are going to be carbonates, phosphates, hydroxides, oxides, sulfides, and these halides and sulfates. Let's see how this works. Look at these and decide if they're going to be soluble or not. Silver nitrate. First thing you say to yourself is, oh my goodness, it's a nitrate. If it's a nitrate, it will be soluble. Magnesium chloride. Well, most metal halides are soluble, except for our heavy metal group. Is magnesium a heavy metal? No. Silver, lead, mercury, and copper are the insoluble ones. Sodium sulfate. The rule says most sulfates are soluble except for barium, lead, and calcium. This is soluble. Silver chloride. Most metal halides are soluble except for the heavy metals. Silver chloride is one of those. It is insoluble. Yeah.
So, why was silver nitrate soluble?
Because it's a nitrate. All nitrates are soluble. Barium nitrate. Nitrate, soluble. Doesn't matter what you pair it with. Nitrates and acetates. We just saw lead-2 iodide. Beautiful yellow stuff. It is insoluble. Silver, lead, mercury, and copper. It's a nitrate. Doesn't matter what's on the other side, it is soluble. Most sulfates are soluble, barium is not. Classic example of a very insoluble salt. Barium sulfate is very insoluble. Iron trichloride. Most metal halides are soluble, except for the heavy metals. Is iron a heavy metal? Nope. Silver, lead, mercury, and copper. Yep.
Good question. Why was magnesium chlorine soluble?
Because it is not one of these heavy metals.
Oh, okay.
And finally, first thing you say to yourself is, what the heck is this? Well, this is acetate. And just like nitrates, virtually all acetates are soluble. Now, if you're being taught general chemistry by somebody that specialized in organic chemistry, this is how you would write it. If you're an inorganic chemist or who knows what, you'd probably write it like this and have no clue what this is. Now, what do you need to know for the exam, right? You need to know the ones that are common. Silver chloride, barium sulfate, lead-2 iodide. Those are the common ones that we work with all the time. Carbonates, phosphates, if they're not group 1 or ammonium, they are insoluble as well. Any questions? Well, let's just look at some reactions. These are all double replacements. Go ahead, fill in the products, and pick out who is going to be insoluble. Silver nitrate is nicely soluble. This is group 1, so potassium carbonate is nicely soluble. Silver carbonate, however, is not. That will be our insoluble product. Let's balance this equation. We have 1 silver, we have 2 silvers. 1 nitrate, 1 nitrate. Let's double this. That gives us 2 silvers on this side, that's what we need. 1 carbonate, 1 carbonate, 2 potassiums, we need a 2. Our insoluble product here is going to be copper carbonate. Again, unless it's governed by rule number 1, that's a group 1 or ammonium, carbonates and phosphates will be insoluble. So, we will make copper 2 carbonate as our insoluble stuff. Balancing, 2 nitrates, only 1 nitrate. We now have 2 potassiums, 1 carbonate, 1 carbonate, 1 copper, 1 copper. I think we're good. Silver carbonate will be our insoluble stuff. I'm sorry, that's aluminum. Standing too close to the board. Aluminum carbonate is insoluble, and so is silver carbonate. But balancing, we have 1 aluminum, 2 aluminums, let's double that. There it goes. 2 aluminums down, 2 aluminums there. We have 3 carbonates here, only 1 on this side. Oh, we also have 6 nitrates on this side, and now 3 carbonates. So I think that does it. Now these were easy because they were all carbonates. silver nitrate, magnesium chloride. They're both soluble. Our insoluble stuff will be the heavy metal silver chloride. All right. To balance this, we have two chlorines here, one on this side. Let's double that, like that. We have, when we put the two there, that gives us two silvers. We need a two there, and I think we're good. Barium sulfate. Barium sulfate is going to be very insoluble. Now, barium sulfate is a real problem in the western states because you pump water from very deep underground, right? Because there's not too many Great Lakes there. So you pump water from deep underground. Under high pressure, barium sulfate is much more soluble than it is at atmospheric pressure. So as this stuff pumps up, barium sulfate precipitates out. Clogs your pump, it's ugly. All right, so we're going to make barium sulfate. Now to balance this, we're going to need two nitrates here. We have a barium and a sulfate here. I think that's okay. Two nitrates. That'll also give us two sodiums. Yep. And finally, the insoluble product here is going to be lead sulfide. Remember, most oxides, hydroxides, and sulfides are insoluble. So we're going to get lead to sulfide. We have two sodiums, only one sodium. We need a two here. We have two nitrates. That'll take care of the two nitrates. One lead, one sulfur. That's all we need. It's just a two. Any questions? See, balancing can actually be fun. It's like doing jigsaw puzzles or crossword puzzles or whatever. Google or Wordle, that's what it's called. Whatever. Let's talk about redox reactions. Again, redox simply says it's an oxidation reduction reaction. We have electron transfer between a donor and an acceptor. One element will go an increase in oxidation number, the other will go a decrease. Now, in order to increase your oxidation number, what do you have to do? So if you're going from 0 to +2, what happens to your electrons? We're losing them, right? The way I remember this, because I get confused all the time, is simply oxidation is loss of electrons. Easy thing to remember. All right, oxidation numbers. The ground state, when you dig these guys up, this is what you get. These are all defined as 0. Just like we said in chapter 3, if you have a binary ionic compound, the oxidation number and the charge are the same thing. Magnesium is +2, bromine -1, so are their oxidation numbers. Lithium phosphide, lithium is +1, phosphorus -3, and so are the oxidation numbers. So if it's a simple ionic, all you do is look at the charge. All right. It is not a simple ionic. If it's molecular, you need rules again. We saw these rules briefly in chapter 3. I said you didn't need to know them then. You kind of need them now. Elements are zero. Group 1 is +1, group 2 is +2. Fluorine, most electronegative element, is always -1. After this, it gets a little interesting. Hydrogen can either be -1 or +1. If it's compounded with a metal, it's -1. Non-metal, +1. Oxygen, almost always -2. Halogens, -1, unless they're bonded to oxygen covalently. Then they're not. So for selenium, we're -2, except in compounds with oxygen. So let's see how this works. SO3. The rule from chapter 3. Oxygen is going to be -2, right? We have 3 of them. That's 6 negatives. To make this neutral, sulfur must be +6. Now that's simple, isn't it? Nitric acid. We will use nitric acid in the lab. Be careful. Concentrated nitric acid especially leaves really bad brown stains on your skin. It burns. All right, here we have a hydrogen connected to an oxygen. Remember, hydrogen can be +1 or -1. If it's bonded to a nonmetal, it'll be +1. So our oxygen is going to be -2. Hydrogen will be +1 because it's bonded to a nonmetal. We have 6 negatives, 1 positive, carbon nitrogen in the middle, must be +5. All right, let's do a tutorial here. This one's a little confusing, maybe. Assigning oxidation numbers. Well, this one's an easy problem. Okay? Because this is an ionic compound containing lead. We remember that nitrate is -1, which means our lead is going to be +2. Simply enter your +2 there, and you're good. Hydrogen in pH 3. Phosphorus is a nonmetal. Therefore, the hydrogen will be +1. We have 3 of them. So the phosphorus must be, where is it? There it is, -3. Any question? All right. In redox reactions, one of the things you do is to look at a reaction, decide if it's redox, have oxidation numbers changed, and then you decide who has been oxidized and who has been reduced. Remember, oxidation is loss of electrons, reduction is gain. If we're going from 2 to 3, we're losing an electron. This has been oxidized. If we go in from 0 to -1, that's reduction. Look at this reaction. Aluminum metal, iron 3 oxide, iron metal, aluminum oxide. Let's see. The elements, both of them are going to be 0. Oxygen will be -2, which makes the iron +3. The products. The element will be 0. The oxygen will be -2. Aluminum is group 3, it'll be +3. So number 1, have oxidation numbers change? Yes. 0 +3, +3 to 0. So yes, this is an oxidation reaction, oxidation reduction. Who has been oxidized? Who has been reduced? Which of these guys have lost electrons? Iron started off as 3, went to 0. To do that, it has to gain electrons, doesn't it? Aluminum was 0, wound up as +3. It had to lose 3 electrons. Aluminum has been oxidized, iron has been reduced. Now, I would love to just stop right here with the discussion of oxidize and reduce. But general chemists don't think that way. They like to make life complicated. And so, in a reaction like this, they define what's called an oxidizing agent. That's the thing that causes the oxidation, and that's the iron. They also define a reducing agent, which causes the iron to be reduced, and that's the aluminum. I will never ask you these guys, but if you get a more advanced chemistry course, yeah, they'll throw this out just to confuse the heck out of you.
We like her.
All right. Here's our redox reaction. We saw this on slide static at the beginning of lecture. This is thermite, the thermite reaction. These are 2 flower pots. This one's full of sand. This one is full of aluminum mixed with iron 3 oxide, the 2 solids. Flower pots have a hole in the bottom, don't they? For water to come in. So there's a little hole in the bottom of this. What we're going to do is come up with a piece of burning magnesium, quickly stuff it in, and then run far away. And the reaction starts. These sparks are little bits of molten iron. And they go everywhere. As it's going, you look at the bottom here, the little hole. See the dribbles coming up? That's molten iron. And you never quite know when the reaction's done. So you just gotta stand back and wait for it. All right, when it is finally done, this is white hot iron in our sand. When it cools off, it looks like regular iron. really fun reaction to do. Now, as with things that are fun in chemistry, people have found ways to make these not fun at all. Thermite is the incendiary in what's called a thermite bomb. And you fly over and drop these on people's homes, and the thermite reaction happens. Not a good thing. This is a neighborhood in London after a German attack in World War II. Pretty bad. We were also just as bad. Remember Dresden? Yes, we started a firestorm with these guys. Anyway, the reaction is fun though. Just don't make bombs. All right. Are these going to be redox or not? And who has been oxidized? Who has been reduced? Tantalum is an element. So is bromine. Over here, bromine will be -1, making the tantalum +5. Who has lost electrons? Tantalum went from 0 to +5, that is oxidation. Tantalum has been oxidized, bromine reduced. Look at this guy. First of all, this is a single replacement, isn't it? The semi-metal has replaced the metal. The non-metal winds up here. All right. Aluminum, group 3 +3, oxygen -2, silicon 0, aluminum 0. Aluminum has gone from +3 to 0, silicon 0 to +4. To me, that's always the easiest one to identify. This has been oxidized, aluminum reduced. Here's another one. Sodium sulfide, lead nitrate. We get lead sulfide and sodium nitrate. This is a double replacement, isn't it? I didn't show it, but lead sulfide will be insoluble. All right. Sodium +1, that's -2. Lead is +2. Over here, lead is still +2. -1, nitrate is -1. Here I broke down the nitrates to +5, -2, whatever. So, who has been oxidized? Who has been reduced? Nobody. Nobody. That's because this is a double replacement reaction. They never involve redox. Finally, nickel 2 chloride plus hydrogen. The elements are 0. Nickel is +2, chlorine -1, hydrogen is +1. We have gone from 0 to +1 for our hydrogen. That means it has lost an electron. Hydrogen has been oxidized, nickel reduced. Any questions, guys? All right, this is the tutorial everybody hates because it is so darn confusing. First of all, these are called half reactions. In a half reaction, you only show the reacting species. So we don't care if this is sodium or potassium or whatever. That's called a spectator ion. All we're interested in for like the VO2 and the VO2 plus are the ions themselves. So that's a half reaction. All right. We want to know if the vanadium here is oxidized or reduced. Now VO plus 2 is a polyatomic ion. So the oxygen, will be -2. To make this whole ion +2, the vanadium must be +4. We have 2 negatives. This must be +4. VO2 with a plus charge. Once again, the oxygens will be -2. In order for this to still have a plus charge, the vanadium must be +5. So, -2 +5. So vanadium has gone from +4 to +5. Does that mean it gained an electron or lost one? It lost one. It has been oxidized. On Blackboard, there are a whole bunch of these obscure things. I apologize. Here's another version of the obscure one. It's even simpler. Here's a thorium reaction. Goes from +4 to 0. Thorium here is an element at 0. To go from +4 to 0, what do? You gain 4 electrons, and that's reduction. All right, to finally wind up the chapter here, we're going to talk about what's called the activity series. When we talked about elements in general, we said that the group 1 metals were so reactive, if they touch water, they burn. These guys will react with acids. These guys are very unreactive. Hydrogen is right here, in between acid and unreactive. So, here we have an equation, sodium reacting with hydrogen to give sodium ion and H2 gas. Sodium way up here, hydrogen way down here. The higher it is, the more reactive it is.
Glorious, nice.
Now, in a single replacement reaction like this, if the element is more active than the ion, sodium the element, that's the ion, then this reaction will go as written. If it's the other way around, it won't work. For example, silver plus copper. Silver is our ion, copper is our metal. They're in the highly unreactive area. The copper is slightly more reactive than silver. So, copper is more active than silver, and metal is more reactive than the iron. The reaction will go as written. We're going to do this in lab, sort of. This contains copper nitrate. I'm sorry, silver nitrate. This is copper wire. You pop them in together. After a couple minutes, you notice this gets really fuzzy. The reason it's getting fuzzy is silver metal is being deposited on the copper. Our solution slowly turns blue because copper salts are generally blue. And we get lots and lots of silver being produced. Why is it blue? Because this is now copper nitrate in solution. Any questions? Metal, iron. Where will this reaction go? Well, we find iron. We find copper. The metal is more reactive than the iron. The reaction will go as written. If you take an iron nail and stick it in a solution of copper salt, you will get copper metal deposited on the iron nail. So on an exam, what does this look like? You get two reactions. One of these works. Which one? Aluminum and lead. Aluminum, way up there, lead way down here. The metal, the iron. If the metal is more reactive than the iron, the reaction goes as written. This one, the iron is more reactive than the metal, and that doesn't work. Okay, speaking of exams, here are some old exam questions. Aluminum and chlorine react to form a compound. What is it? Well, we can make a guess. This would be our equation. A, the compound will be ionic. Of course it will. It's got a metal. That's good. Oxidation number of aluminum is, the reactants is 0. It's an element. Of course it is. Molecular formula is most likely AlCl3, group 3, group 7. Yep, that works. It's an ABC. Which of these are insoluble? Well, barium sulfate, classic. Very insoluble. Lead 2 iodide, beautiful yellow solid. This is a nitrate. Nitrates are soluble. It's an A. Lead plus fluorine, you give lead fluoride. Synthesis reaction, right? What happens to the oxidation number of fluorine? Well, that's an element. It's 0. This is fluoride anion, it's -1. We've gone from 0 to -1. A changes from 0 to -4? Nope. Does not change, that's wrong. Minus 1 of the reactions goes to 0. None of the above. On the exam, you will probably get something like this to fill in oxidation numbers. We can do that. Oxygen will be minus 2. We have 10 negatives. Nitrogen, to make it neutral, must be plus 5. Another one, this is chlorous acid. Hydrogen, well, it looks like this. Hydrogen is bonded to an oxygen, so it will be plus 1. Oxygen will be minus 2. Hydrogen plus 1. We have 6 negatives, 1 positive. Chlorine is plus 5. All right. We have 3 tutorials. Do them on Blackboard. Balancing, assigning redox numbers, and oxidation, reduction reactions. Now, you all have your exam scores. I'll give the exams back on Wednesday. And some of you are probably sitting back saying to yourself, gee, I need 160 points to be making an A. And I don't. And gee, I wish I would have done more tutorials. Well, I'm going to give you yet 2 more reasons to do tutorials. After you complete exam 2, if your total score is 350 or above, on the spot, I will give you an A, and you will not have to take the final. As we're saying again, you must complete exam 2. Your overall total points must be 350 or above. You get an A on the spot, and no final. Oh my goodness.
Thank you so much.
And this is worth saying again as well.
Basically, please do them.
Please do the tutorials. Now, I will tell you this is a secret, don't tell anybody. If you had not finished all of the tutorials you wished that you had in the first half, those are gone off Blackboard, right? After we finish chapter 9, I will have what I call amnesty weekend, and I will put them back up for Friday, Saturday, and Sunday. Okay? So something to look forward to. Remember, lab on Wednesday, and again, it's reactions. Okay, guys, have a good day.